In this video, I will talk about the vibrations. First of all, let us see what are the types of vibrations. There are three types of vibrations. The first one is longitudinal vibration. This means, let us say one bar is there here like this, and if we apply any disturbing force in this direction along the axis of the bar, and this bar tend to vibrate in this direction along the axis of the bar, and this kind of vibrations we are calling as the longitudinal vibrations. And the next one is the transverse vibrations. Transverse vibrations. Transverse vibrations means for example, this is the bar. This is the bar which is fixed here, and if we apply any force in this direction, that is the transverse direction. Transverse direction means perpendicular to the axis of the beam, and this bar will try to vibrate in this direction like this, and these vibrations we are calling as the transverse vibration. And the third one is the torsional vibrations. Torsional vibrations. Torsional vibrations means let us say one bar is there like this, the similar kind of bar. This could be either rectangular cross section or circular cross section, anything is irrelevant. But if you twist this like this along about the axis of this bar, if you are twisting like this circularly and leave it, and it will try to vibrate in this direction like this in a circular fashion, and those vibrations we are calling as the torsional vibrations. Now let us see what is a natural frequency of vibration. Natural frequency of vibration. For example, one bar is there, and we are disturbing this bar in the longitudinal direction like this. That means we are just pulling this bar and leaving it, and it will tend to vibrate in this direction like this. And it will have some maximum displacement. We are calling that one as x. And if we plot this displacement with respect to time, this is the time axis, and on the y-axis we have the displacement, which is x small x. Okay, we will get a curve something like this. Initially at time t equal to 0, here is t equal to 0, we don't have any displacement here at this location, but after disturbing it, it has started displacing like this. That means its amplitude, its displacement is increasing and reaching its maximum position. That means this extreme position, we are calling this maximum displacement as x, which is the amplitude of vibration. Okay, and if we write this as an equation, x is equal to capital X sine omega t, where omega is called the natural frequency. Omega is called the natural frequency. For example, if we want to find out the natural frequency of any object, longitudinal natural frequency, actually for this single bar, if you disturb in this longitudinal direction, we will get the longitudinal natural frequency of this bar. Similarly, if you apply the force or the disturbing force in the transverse direction, we will get some other natural frequency because the stiffness is different here in that case. It is very important to find out the natural frequency of any system before we design any machine component or any civil structure. It is very important to know the natural frequency of the system, because if we operate the system at the natural frequency, that tend to resonance, which is a catastrophic failure. So it is very important to find out the natural frequencies of the system. Now let us try to find out the natural frequency of a simple spring mass system. Here in this case, this is the spring, okay, and after application of the mass, we are attaching some mass to it, then it will deflect, it will come to this location. This is the mass. After attaching mass, it is elongated. It came from its original length is here, but after attaching the mass, it has reached this location. This one we are calling as the static deflection, delta static. Okay, if the stiffness of the spring is K, okay, now let us try to draw the free body diagram for this mass. If this is the mass, this is the mass, at the center of gravity mg is acting, and spring force is acting in the upward direction. This mass is supported by this spring, and the force, the spring force, is nothing but K into, that is the stiffness of the spring into delta static. So K into delta static is equal to m into g. Okay, this is the one equation. And also now after attaching the mass, this is our mean location, and if we just pull it and leave in the axial direction, it will vibrate in this direction like this. And let us say these two are the extreme positions. This is the mean location, mean, and this one is extreme, and this one is another extreme, and we are calling this one as the amplitude of vibration, which is capital X. Okay, here at this location we will have, in the mean location, we will have the maximum velocity. That means we will have the maximum kinetic energy at mean location, maximum kinetic energy, maximum kinetic energy at mean location. that must be equal to, at the extreme location we will have uh, zero kinetic energy, because at the extreme location velocity is 0, half mv square, in that velocity is 0. So the kinetic energy must be 0 at the extreme location, but the potential energy, whatever the kinetic energy is there at the mean location, will be converted to the potential energy of the spring. So that equal to the maximum potential energy P, maximum potential energy P in the spring. Okay, so maximum kinetic energy at the mean location. Now we know that the displacement equation for this spring mass system is x is equal to capital X sine omega t, and if we want to find out the velocity, dx by dt is equal to x dot is equal to x omega into cos omega t. And if we want to find out the acceleration, d square x by dt square is equal to x double dot is equal to minus x omega square into sine omega t. Now we want to find out the maximum kinetic energy. Maximum kinetic energy is nothing but half mv square, half mass into velocity max, v max square. This is the maximum kinetic energy, which is equal to half k into stiffness into x square, x max square, x max square. That is the maximum displacement of the spring. This is the potential energy in the spring, the maximum potential energy in the spring, and this is the maximum kinetic energy in the spring. Okay, these two must be equal, because at whatever location the sum of the kinetic energy and potential energy must be 0. So derivative of PE plus KE, sum of the potential energy plus kinetic energy must be 0, because this is constant. If you derive the constant, you will get the 0. And we know that at the main location the displacement is 0, so the potential energy in the spring is 0. So the maximum kinetic energy at this location must be equal to the maximum potential energy of the spring at extreme location. So this is nothing but half mass into v max. V max is, this is the velocity equation. V max is nothing but the maximum value of this one is at cos omega t value is 1, right? So the maximum velocity will become x omega m into x into omega whole square must be equal to half k into x max. What is the maximum displacement? That is nothing but the amplitude, capital X square. If we solve this equation, we will get omega square is equal to k by m, and omega is square root of k by m, and this also can be written as square root of g by delta, g by delta static. If you use this equation, k by m can also be written as g by delta static. Now let us see some of the natural frequencies. Let us say this is the bar. If we want to find out the natural frequency, longitudinal natural frequency of this bar, that means if I just disturb it in this direction and leave it, with what frequency it is going to vibrate. If I want to know that, the natural frequency omega n is nothing but square root of k by m. We just have seen that. Okay, but here in this case, the for the bar we have to find out what is the stiffness, that is longitudinal stiffness of the beam. Is we know that the deflection caused in this spring is equal to P into L by AE. We know that. Okay, so the stiffness is load per unit deflection, that is P by X, is nothing but A into E by L, AE by L. So this will become the stiffness of a bar. If we replace the same thing, we will get square root of AE by L into M. This will become the natural frequency of a bar. This is the longitudinal vibration. This is the frequency with which it will vibrate in a longitudinal direction. For example, for the same bar, let us say we are applying force in the transverse direction, in this direction. That means we just applied force in this transverse direction, that is perpendicular direction to this longitudinal axis. In that case, here also again the formula is same, omega n is equal to square root of k by m, but here in this case the stiffness can be obtained as, we know the deflection x here in this case can be written as P into L cube by PL cube by 3EI. This we would have studied in strength of materials. So load per deflection P by X can be written as 3EI by L cube. E into I by L cube. I is the moment of inertia, E is the Young's modulus, L is the total length of the bar. This is the length of the bar. So this is nothing but load per unit deflection is nothing but the stiffness. The stiffness of a bending beam is nothing but 3EI by L cube. So if we use this value here in this equation, omega n is nothing but square root of k is nothing but 3EI by L cube into m. This is the natural frequency of the bar for transverse vibrations. This is for transverse vibrations. And this is the natural frequency for longitudinal vibrations. Now let us see about the torsional vibrations. Let us consider one circular bar Okay, and if we just twist it and leave, twist it about the axis of the shaft, okay, and if we just leave it, and it will try to vibrate in this direction. To find the frequency of that vibration, here also we are using the same formula, omega n is equal to square root of k by m, but here k is the torsional stiffness. To find out that, we can use the basic torsion formula, T by J equal to G pi by L, where G is called the rigidity modulus, and pi is the angle of twist, and L is the length of the shaft, and J is the polar moment of inertia, and T is the torque with which we are applying. Okay, T by J equal to G pi by L. Okay, torque per unit deflection is the stiffness in this case. T by pi is equal to GJ by L, G into J by L. Okay, so our omega n can be written as square root of k by m. K is nothing but G J by L into m, square root of k by m. So this will become the natural frequency in case of torsional vibrations. Now we know that for any spring of stiffness k, if we attach a mass and if we deflect, if we disturb in this direction, that is the longitudinal direction, in this direction it is going to vibrate in this direction like this, and the frequency of vibration omega n is square root of k by m. Here in this case we are not considering the mass of the spring. If we want to consider the mass of the spring, what is the natural frequency, new natural frequency, if we want to find out, let us say the mass of the spring is ms. Okay, now we want to find out what is the natural frequency of this system considering the mass of the spring. Okay, now let us consider a small strip of the spring at a distance of y and the length as dy, and try to find out what is the kinetic energy of that strip only. Okay, and let us say mass per unit length of the spring, mass per unit length of spring is equal to m dash. M dash is the mass per unit length of the spring, and L is the total length of the spring. Total length of the spring is equal to L. Otherwise we can say that m dash into L is equal to mass of the spring ms. Okay, now the kinetic energy of the element that small element is nothing but half mass of that element. Mass of the element is nothing but m dash, this is the mass per unit length, into dy. Dy is the length of the element, this is the mass of the element, into velocity of the mass, into, but we want to find out the mass of the element. If we have the total velocity of the mass is v, here at this location the velocity is v, and here we have the velocity 0, and the velocity will be increasing linearly. So at this location we will have some velocity, and that velocity is nothing but v into that velocity of element is nothing but v into this distance is y by the total distance. From the similar triangles you can get this equation, it's very easy one. This is the total length, okay, v into y by l. This is the velocity at the element. So this is v into y by l, this is the velocity at the element, half mv square. This is the kinetic energy of the element, but if I want to find out the kinetic energy of the entire spring, I have to integrate it within the limits. This y is varying within the limits 0 to L. Okay, now after integration we will get half m dash, all these are constant except y square. I'm taking it out of integration, v square by l square into y square dy. Integration is y cube by 3, and after application of this limits we will get l cube by 3. This is nothing but half one by 3 into half m dash into l into v square. This is nothing but, this can be written as half m dash l is nothing but ms by 3 into v square. Okay, so in place of m we got ms by 3. So if we want to consider the mass of the spring, we have to divide it by 3. So the new natural frequency of the system will become square root of k by m plus ms, mass of the spring, by 3. This is the new natural frequency if we want to include the mass of the spring also. The same thing is applicable to the bar also. Let us say one bar is there, which is attached to some mass. Okay, the mass of this one is m1, let us say, and the mass is here. Okay, and if we just disturb in this direction, longitudinal direction, we just have seen that it is square root of k by m, where k is ae by l. It's k is nothing but ae by l. So the natural frequency omega n will become square root of k is nothing but ae by l. In place of m we have m plus m1 by 3, where m1 is nothing but the mass of the bar. Okay, now let us see the equivalent stiffnesses. Equivalent stiffness. In case of springs connected in parallel, like this, and we are applying force like this, this is nothing but the springs in parallel direction. Let us say this is k1 and the stiffness of spring 2 is k2, and we are applying force F in this direction. In this case, whatever the force we are applying is shared by spring 1 and spring 2. So the force whatever we are applying, F is equal to F1 plus F2. Okay, let us say it is deflected by an amount x here in this case, so the total deflection k equivalent into x is equal to k1 into x plus k2 into x. Here actually force is divided, but the displacement is same for both spring 1 and spring 2, okay, in parallel case. So k equivalent can be written as k equivalent is nothing but k1 plus k2. That means we are increasing the strength of the beam by connecting parallelly. Okay, this is about the equivalent stiffness if they are connected in parallel. Now let us see what if they are connected in a series. This is k1 which is connected in a series. Let us say this is k2 and this is k2, and this here is k1, and we have force here F. Okay, here in this case force is same. Whatever the force we are applying here, F, this k1 is also seeing that same force and k2 is also seeing the same force, but the final deflection we are getting delta, whatever that is, x or x, is nothing but at the force application of force. The total deflection at this location is nothing but the deflections in individual springs x1 plus x2. Okay, and we know that F is equal to k into x. F is nothing but k into x. If you want to find out x, it is F by k. Here x is nothing but F by k is nothing but k equivalent here, which is equal to here also F by, for x1 it is k1 plus for x2 it is F by K2. So our K equivalent here in this case, here actually force is same, here force is same, force is same, force is same, but the deflection is divided between these, deflection is divided, like x1 x2 between these two springs. But here if you see, deflection is same, but the force is divided as F1 F2, force is divided between the two springs, okay. So F will be cancelled here, and the K equivalent is nothing but K1 K2 by K1 plus K2. If the stiffnesses of the both springs is equal, and it is equal to K square by 2K, this is nothing but K by 2. That means the stiffness is decreasing, that is the strength of the spring is decreasing by connecting in series. If we connect the springs in series, the effective stiffness will reduce, but if we connect in parallel like this, the effective stiffness will increase. For example, if we assume any mass here M, and here one more mass M, okay, let us say these both are of same stiffness and it is equal to K. In that case, it will become K equivalent will become 2K, and the natural frequency omega n will become square root of 2K by M. But here in this case, the springs in series case, omega n is equal to square root of K by 2M. Now let us try to find out the natural frequency of this spring mass system. Here is the mass, and through pulley arrangement we are connecting the springs like this. Let us say the stiffness of the each spring is the same thing, that is K, and K. Now we want to find out the natural frequency of this spring mass system. The omega n for this case is nothing but square root of K by M. This also can be written as square root of G by delta static. Here in this case, delta static is nothing but, let us try to find out what is delta static in this case. Delta static. Now let us try to draw the free body diagram of this pulley. In this pulley, mg is acting here like this, as the mass is attached here. Okay, this mg is to be balanced through these two wires like this, So if it is mg, this must be equal to mg by 2. This also must be equal to mg by 2. So the force in this is nothing but mg, force in this spring, because this is mg and it is connected to mass like this, and the force in this spring is mg by 2, and in this spring is also mg by 2. So if we want to find out the deflection in this spring, is nothing but, since F is equal to K into X, the deflection is F by K. The force in this is mg, force by K, right? mg by K. And this mass will have the static deflection due to these springs also, so the deflection in these two springs is nothing but mg by 2. This is the force, mg by 2 is the force by K. So mg by 2K plus mg by K will become the static deflection in this case. So this is nothing but 3 by 2 times mg by K, and omega n is equal to square root of g by delta static, is nothing but, we will get 2K by 3mg. This is nothing but square root of 2 by 3 into K by m. This is the natural frequency of the system. This is the frequency with which it will vibrate, upon disturbing this mass. Now let us consider one more example to find out the natural frequency. This is just similar to the previous problem. The only difference here is there is no spring here at this location, but we have spring on only one side. The stiffness of this spring is K, and here we have one more spring with stiffness K. Now we want to find out the natural frequency of this system. Now omega n is nothing but square root of g by delta static, and if we want to find out the delta static, similarly in the just as the previous case, we just draw the free body diagram for this pulley. Okay, since m is attached here, m will be acting like this, mg, and these two forces must be equal to mg by 2, and here also mg by 2. But here so the deflection in this, since f is equal to kx, x is equal to f by k, that means the force in this spring by K will give me the deflection in this spring. The force in this spring is nothing but mg by 2 into K. But here the static deflection of this mass is nothing but the deflection here and the deflection here. The deflection here will be just distributed along this, so the total downward movement of this pulley due to this spring is nothing but the total deflection in this spring by 2. So I am adding one more 2 here, okay, plus the static deflection of the spring to get the total deflection of this mass, right? So the force in this mass is nothing but mg, this force mg by K. K is nothing but the same thing, K here, which is nothing but mg by 4k plus mg by k. This is nothing but 5 by 4 mg by k. So our the natural frequency omega n will become, or natural frequency omega n is nothing but omega n is nothing but square root of g by delta static 4k by 5 mg. This is nothing but square root of 4 by 5 k by m. This is the natural frequency of this system, spring MOS system. Now let us try to find out the natural frequency of this system. This is a rigid bar. This one is the rigid bar which is hinged at one end, that is it can freely rotate about this hinge, but we are supporting this bar using this spring of stiffness K1 which is fixed at a distance of L1. Okay, and this total length of the bar is L2. Okay, now we want to find out the natural frequency of this system, that is if you just disturb this mouse, with what frequency it is going to vibrate. If you want to find out that, let us try to draw the free body diagram of this bar. Okay, let us say this is F1 and this is F2 and this is L2, and due to the spring there is upward force, that is F1, which is acting at a distance L1. Okay, this force F2 is trying to rotate this bar in clockwise direction, which is opposed by this moment, which is counterclockwise moment in this spring. So from the equilibrium of moments we can write that F1 L1 must be equal to F2 L2. This force into distance must be equal to this force into this distance. So F1 is nothing but F2 into L2 by L1. But we know that F2 is nothing but the force in this location, at this location, which is nothing but mg. F2 is equal to mg. So our static deflection, delta static, is equal to the deflection in this spring. We have the equation F is equal to k into x. If we want the deflection, force by k, the force here in this case is nothing but mg by k is nothing but k2 plus the total deflection. In this case actually this mass is coming down not only due to this spring but also this spring. This is coming down by an amount mg by k2 in this spring, in the second spring, but in the first spring also there is a deflection, and that is equal to F1 by K1. F1 here is nothing but F2, here F2 is nothing but mg. So this will become mg into L2 by L1, L2 by L1. This is the deflection L1 into K1. Force by K is the deflection in this spring at this location. This whole thing into L2 by L1. Just erase this. This is L2 by L1. This is nothing but mg by K2 plus 1 by K mg into L2 by L1 whole square. Here I have used this, it is because it is going to deflect like this, something like this. Let me draw here. The bar is like this and it is deflecting like this, and if there is a deflection of F1 by K here, the deflection here must be the deflection here, that is F1 by K into L2 by L1. That is the maximum deflection it can have due to this spring 1. So I have divided with L2 by L1 again, sorry, multiplied with L2 by L1. So this will become the total static deflection of the spring. So our natural frequency omega n is equal to square root of g by delta static, which is equal to square root of 1 by m into 1 by K2 plus 1 by K1 into L2 by L1 whole square. This will become the natural frequency of this system.